an atom and felt like there are these hidden mathematical patterns woven into everything. You see spherical symmetry everywhere. Planets, stars, down to tiny particles.
It's really striking.
It makes you wonder, is there some core mathematical key that helps us understand how things behave when they have this, well, perfect spherical shape?
That's a great question.
That's exactly what we're trying to get to the bottom of today. We've been digging through a stack of sources, really focusing on a deep dive into spherical harmonics, classical ways to quantum shapes.
And what's truly fascinating here, is how these mathematical functions, these spherical harmonics, they aren't just abstract ideas someone dreamt up. They fundamentally emerge directly from the physics and the geometry of systems that have spherical symmetry.
So they come from the situation itself.
Exactly. It's a journey that, maybe surprisingly, connects things we can see, like vibrations, to the invisible probabilistic world of quantum particles.
Okay, so our mission today is to really unpack these sources. We want to understand what spherical harmonics actually are.
Right.
See how they naturally describe classical waves on spheres, and then make that incredible leap, figuring out how they turn up again in the quantum realm to define atomic structure and, where else they pop up.
Should be interesting.
Get ready for some connections and hopefully some genuine aha moments for you listening. Okay, let's start at the beginning then. Where does the idea of spherical harmonics even come from in physics? The sources seem to point to simple classical waves.
Precisely. Yeah. Think about vibrations on the surface of, say, a balloon or sound waves inside a perfectly spherical room.
Okay.
To describe these mathematically, you'd use the wave equation. But dealing with a sphere in standard XYZ coordinates is, well, it's a nightmare.
Right. Doesn't seem natural.
You pretty much have to use spherical coordinates, r for the distance from the center, for the angle down from the vertical axis, and for the angle around that axis.
Okay, r, theta, phi. Got it.
The wave equation involves something called the Laplacian operator.
Right, I've seen that. Measures curvature.
Sort of, yeah. How much a function spreads out or curves. Writing that in spherical coordinates looks complicated at first glance. But it's structured in this really brilliant way that lets you cleanly separate the part that depends only on distance, on r, from the part that depends only on the angles, a and r.
Okay, that's the magic phrase I saw mentioned, separation of variables.
That's the one.
So it's like taking this really complicated 3D problem and carefully taking it apart.
Exactly, like disassembling a machine.
Into simpler 1D pieces so you can understand each bit individually.
Precisely. That's a great way to think about it. You assume the solution for the wave can be written as a product, a function of r times a function of or times a function of.
Okay.
You plug that into the wave equation, and because of how the Laplacian separates, you end up with 3 simpler equations, one for each coordinate.
Makes sense.
The important part for spherical harmonics is the angular part, the equations for the Hopf components combined. This is where they're born, essentially.
From the angular equation.
Yes, and here's where physics and geometry step in and lay down the rules.
The boundary condition?
Exactly. The solution for the part that depends on the angle around the z-axis, it must be single-valued.
Meaning?
Well, think about walking around the z-axis. If you're at angle and you walk another full circle, 2 radians...
You're back where you started.
Right. You're at the exact same physical spot. So the wave's value must be the same at n plus 2.
Okay, that makes physical sense.
This requirement, this boundary condition that e plus 2 has to equal, mathematically forces a constant that pops out of the separation process.
Right.
We usually call it m.
Right.
It forces m to only be able to take integer values. So 0, 1, 2, and so on. It can't be like 1.5.
Just from that requirement of returning to the same value. Wow.
Yep. Then you solve the equation for the a part, the angle down from the pole. That equation is known as the associated Legendre equation.
Okay.
Here, the physical constraint is that the solution has to be physically sensible everywhere. Specifically, it has to be finite, not infinite at the poles, where still is 0 and yo is...
Can't have infinite waves at the North Pole.
Exactly. Applying this finiteness condition to the solutions mathematically restricts the other separation constant, which we call O.
Another constant.
Yes. And it restricts O to be a non-negative integer. So O can be 0, 1, 2, and so on.
Okay, so m is an integer. It's a non-negative integer.
And there's one more constraint. For a given value of O, the integer we just talked about is further restricted. Its absolute value, m, can't be larger than O.
Okay, so m goes from O up to plus L in integer steps.
Precisely. For O, M can be ∠1, 0 or 1. For O2, M can be ∠2, ∠1, 0, 1, 2.
Wow. So wait a minute. These specific whole numbers, A and M, they aren't something arbitrary we just picked, right? Or some tweak we made.
Not at all.
They emerge naturally just because the math is describing something on a sphere and the wave has to behave reasonably on that sphere.
Precisely. That's the key point.
Yeah.
They are baked into the problem by the spherical geometry and the boundary conditions needed for a physically real solution.
It's like the sphere's shape itself forces this quantization.
It is. It's a form of natural quantization, even in classical physics, which is pretty cool.
Okay, so these are the spherical harmonics, the Yam functions.
Well, the Yam functions are the combined solutions for A and Pak. They involve those associated Legendre polynomials for the FAD and the Yam term for the part plus a normalization factor.
And Yam are the labels, the indices?
Yes, the degree and the order identify each specific spherical harmonic.
Okay. And these functions have special properties.
They do. Really important mathematical properties. First, normalization. If you square the magnitude of Yam and integrate it over the entire surface of the sphere, you get exactly 1.
Okay. Why is that useful?
It becomes absolutely crucial in quantum mechanics when we talk about probabilities. It means the total probability of finding the particle somewhere on the sphere is 1.
Oh, okay. Makes sense. What else?
Second, orthogonality. If you take two different spherical harmonics, say Yam and Yam, where either U is an E or M is an M, and you multiply them together and integrate over the sphere,
You get 0.
you get 0. They are independent of each other in this specific mathematical sense. It's like different pure colors in a spectrum or different notes in a chord. They represent distinct patterns.
Like independent modes of vibration.
Exactly.
And the third property, you said it was powerful.
Completeness. This is maybe the most powerful one. It means that any reasonably smooth function you can imagine or measure on the surface of a sphere.
Like temperature on the Earth or...
Exactly. Or gravitational potential or brightness, anything, can be perfectly built by adding up a series of these spherical harmonics, each multiplied by some coefficient.
So it's like a Fourier series, but for a sphere.
That's a perfect analogy, yes. They form a complete basis, a universal language for describing functions on a sphere. The terms with lower a values capture the broad, smooth features.
Like the overall shape.
Right. And the terms with higher and higher values add in the finer and finer details, the sharper variations.
Okay, that makes sense conceptually. But how do we visualize these? What do those numbers Am actually look like on the sphere? How do they shape the function?
Good question. Think of the degree as telling you about the overall complexity or waviness of the pattern on the sphere.
More wiggles for higher A.
Basically, yes. It directly corresponds to the total number of nodal lines.
Nodal lines, places where the function is 0.
Exactly. Places where the function crosses from positive to negative or vice versa. For a given Yam, you get exactly total nodal lines.
Okay, so Am tells you the total number of 0 crossing lines. What about Am?
The order, M, tells you how those nodal lines are arranged, specifically how many of them pass through the z-axis, like lines of longitude. The absolute value, M, tells you the number of these azimuthal nodal lines.
Azimuthal, running pole to pole.
Correct. And the rest of the nodal lines, which is A minus M of them, those must be circles around the z-axis like lines of latitude. Those are the polar nodes.
Okay, so A is total nodes, M is longitude nodes, and M is latitude nodes.
Got it. And we visualize them by plotting the function's magnitude, maybe as a distance from the sphere's center, or using color maps on the surface. The nodal lines are the boundaries between the positive and negative regions, or lobes.
Can we look at some examples, like the simple ones from the source material?
Absolutely. For A is 0, the only possible M is 0, Y0, 0.
Okay, A at 0 means 0 total nodal lines.
Right, so the function is constant everywhere. It's perfectly spherical, no structure.
Which totally foreshadows this orbital shape in atoms, right?
Exactly. Now, for A1, how many total nodes?
1. A1 means 1 nodal line.
Good. Now, M can be 0 plus 1 or metaphun. If M owes 0, what's it?
0.
So 0 azimuthal nodes. How many polar nodes?
M is 1, 0 owes 1 metic 1.
One polar node.
And a polar node, a line of latitude where the function is 0, is the equatorial plane, the z-plane. This gives you that dumbbell shape oriented along the z-axis, positive on one side, negative on the other.
The PZ orbital shape.
Precisely. Now, what if M1, so M plus 1 or M1?
Okay, M1 means one azimuthal node, one line running pole to pole.
And polar nodes.
M is 1, 1 is 1, 1 equals 0,
Yeah.
0 polar nodes.
Right. So you get a nodal plane through the z-axis, and linear combinations of the m+1 and m1 solutions give you the px and pi orbital shapes, with nodal planes along the yz and x planes, respectively.
Got it. P orbitals have one node. And for E2.
2 total nodal lines or surfaces. The math naturally leads to those d orbital shapes.
The cloverleaf ones and the dumbbell with the donut.
Yep, the dumbbell with the torus. Each of those shapes has 2 nodal surfaces corresponding to A2.
Amazing how the shapes just emerge from those NMEM values. And the sources note, importantly, that while the standard mathematical forms, the UM themselves, are complex functions.
Right, they have I in them.
We often use real combinations for visualization, and those real combinations directly match the familiar SPDF orbital shapes you see in chemistry textbooks. The table in the source clearly shows this connection.
Okay, so we've seen how this math describes classical waves and shapes on a sphere. Very elegant. Now, here's the part that really makes you pause. How in the world do these same exact mathematical functions end up describing the tiny, fuzzy, probabilistic world inside an atom? It seems like such a huge leap.
It does feel like a leap, doesn't it? But it's actually a beautiful continuation of the same core principles.
How so?
In quantum mechanics, the behavior of a particle like an electron in an atom is governed by the Schrödinger equation.
Right, the fundamental equation.
Now, for an electron orbiting a nucleus, the main force is the electrical attraction, and the potential energy V for that force depends only on the distance r from the nucleus.
Okay, it's centrally symmetric.
Exactly. Just like the classical examples, this is a system with perfect spherical symmetry.
So, separation of variables again.
You guessed it. When you write the time-independent Schrödinger equation for this system in spherical coordinates and apply that same method, separation of variables.
You get separate equations for the radial part, RR, and the angular part, Y.
Precisely. You get a radial equation, and its solutions, RR, determine things like the electron's allowed energy levels and how far sort of its wave function extends from the nucleus. These solutions give us the principal quantum number n, and they also depend on R.
Okay, N for energy and size. What about the angular part?
The angular equation. And get this. It turns out to be exactly the same mathematical equation we just solved for the classical wave on a sphere.
No way. The exact same equation. Seriously.
The exact same one, which means the solutions, the angular part of the electron's wave function,
Must be the spherical harmonics. The yum?
must be the spherical harmonics ion. But, and this is the crucial difference, the interpretation is now fundamentally different. It's deeply physical in the quantum sense. These functions aren't describing a physical wave height or pressure anymore.
Their probability amplitude.
Exactly, probability amplitudes. And they connect directly to angular momentum.
How does angular momentum come into it?
Well, in quantum mechanics, every measurable physical property, like energy or momentum or angular momentum, has a corresponding mathematical operator.
Okay, like a mathematical instruction.
Sort of.
Yeah.
And for orbital angular momentum, there are operators for the square of the total angular momentum, written L on, and for the component of angular momentum along a specific direction, usually chosen as the z-axis,
Yeah.
L.
L squared and LZ.
Right. And a core absolutely fundamental result in quantum mechanics is that the spherical harmonics YEM are the eigenfunctions of these angular momentum operators.
Okay, eigenfunctions. That's a bit of mathematical jargon again. Can you break down what it means for YEM to be an eigenfunction of angular momentum, maybe in a less dense way?
Absolutely. Let's try. Think of an operator as something that does something to a function, transforms it somehow.
Okay.
An eigenfunction is a very special function. When the operator acts on it, you don't get some complicated new function back. You just get the exact same function you started with.
The same U.
The same U, yes. But multiplied by a simple number. That number is called the eigenvalue.
So the function survives the operation, just gets scaled.
Precisely. So when the L operator acts on a spherical harmonic yom, the result is Ly L plus 1. L. Yeah.
Oh, so the eigenvalue is L plus 1 times h bar squared.
Correct. And h bar is just Planck's reduced constant, a fundamental constant of nature.
And for L's?
When the L's operator acts on yum, you get LZYM equals M yum.
The eigenvalue is m times h bar.
Right. Now, what this means physically is profound. These eigenvalues are the only possible results you can get if you were to actually measure the square of the electron's total orbital angular momentum.
You'd have to get some plus one.
Yes, if the electron is in the state, young m, and if you measured its z component of angular momentum.
You can get Yelmy.
Correct. Those are the only allowed quantized values.
So the classical separation constant, that integer that came from the pole boundary condition, is now the orbital angular momentum quantum number. It tells us the magnitude squared of the electron's angular momentum.
Essentially, yes, it determines the magnitude, and the classical separation constant, m, the integer from the periodicity around the axis,
is now the magnetic quantum number,
Yeah.
telling us the orientation.
Exactly. It tells us the quantized component of that angular momentum along the z-axis. The same integers that popped out of classical geometry are now fundamental quantum numbers describing the electron's angular momentum.
That is genuinely incredible. The connection is so direct.
It is. And this leads straight to the concept of atomic orbitals. The complete spatial description of an electron's state, its wave function, is the product of that radial part, RR, and the angular part, YM.
R times Y.
Right. And the probability density, the likelihood of finding the electron at some point in space, is the square of the magnitude of the wave function, equal R times yen.
And the familiar shapes of the atomic orbitals that we always see in chemistry. Those are essentially visualizations of this probability density, often just focusing on the angular part, the yum part, or those real combinations.
Precisely. You've got it. The s orbitals for R are spherical because Y0 is constant, no angles dependence, no nodes.
Matches you.
The p orbitals for R are dumbbell-shaped with one nodal plane.
Matches O1 having one node.
Exactly. The d orbitals for R2 have those cloverleaf or dumbbell torus shapes with two nodal surfaces.
It matches you having two nodes.
Right. And the complex orbitals for R3 have three nodes. The number of nodes is R.
So it all connects back.
It all connects back. We combine these angular shapes with the principal quantum number n from the radial solution,
which gives energy and size.
Right. So n, n, m, m are the quantum numbers describing the spatial part of an electron's state. And of course, there's also the spin quantum number.
Yeah, it's also minus a half.
Right, which describes an intrinsic property of the electron itself, kind of like an internal angular momentum, not derived from its spatial motion described by the spherical harmonics. The source includes a helpful table summarizing these numbers.
Okay.
But the key takeaway here really is that the shapes of atomic orbitals aren't just pretty pictures somebody drew. They are the direct visual representation of the spherical harmonics,
the Youm functions,
which are the fundamental mathematical functions describing the allowed quantized states of angular momentum for an electron in the atom's spherically symmetric potential.
Okay, so individual orbitals, like the p and d ones, have these specific, often quite directional shapes. But does that mean an atom as a whole, with all its electrons, is not necessarily spherical? Or is it?
That brings us to another really elegant result called Unsold's theorem.
Unsold's theorem, okay.
It states something remarkable. If you take all the spherical harmonics for a specific value of euro, so all the Youm functions, where m goes from yo all the way up to plus o.
Like all the p orbitals or all the d orbitals.
Exactly. And you sum up the squares of their magnitudes,
add up all those probability shapes for a given f.
The result you get is just a constant value. It doesn't depend on the angles or o at all. It's the same value everywhere in the sphere.
Seriously. You add up those directional dumbbell and cloverleaf shapes and you get the sphere.
You get a perfectly spherical distribution. The constant value is actually 2a plus 1 divided by 4.
Wow. Okay, mathematically elegant. But what's the physical consequence?
The profound physical consequence is this. If an atom has a completely filled electron subshell,
meaning all the possible m states for that are occupied, usually by two electrons, each with opposite spins.
Right. Then the total electron probability distribution for that entire subshell is perfectly spherically symmetric. The individual directional orbitals perfectly average out or cancel each other out when you combine them all.
So a filled p subshell or a filled d subshell makes that part of the atom's electron cloud spherical.
Exactly. And this also holds true for certain half-filled subshells, which adds another layer of interest.
Okay, that's neat math, that these directional shapes add up to something spherical. But why does that matter physically? What does having a perfectly spherical electron cloud do for an atom?
Oh, it matters hugely for predicting atomic properties and especially how atoms interact.
How so?
Atoms are ions with fully filled outer electron shells. Think of the noble gases like neon or argon, or sometimes those stable half-filled shells.
Like manganese or zinc groups.
Right. They are incredibly stable and generally unreactive. Why? Largely because their overall electron distribution is this highly symmetric, closed spherical configuration. It's energetically very favorable, and there aren't really any lopsided regions of electron density reaching out, eager to interact or form bonds.
So the symmetry leads to stability.
Very much so. And this spherical symmetry also makes it much simpler to model how these atoms or ions interact with their surroundings in liquids or solids or gas phase.
Okay. And conversely, atoms without filled shells.
Conversely, atoms with partially filled subshells that aren't spherically symmetric overall, think of carbon with its partially filled p shell, or oxygen, or transition metals with partially filled d shells.
Yeah.
They don't have this overall spherical symmetry in their valence electron cloud. The specific directionality of those individual occupied orbitals, those p or d shapes, dictates where the electrons are most likely to be found, and therefore where the atom is most likely to form bonds with other atoms.
So the orbital shapes dictate the bonding geometry.
Absolutely. This is why carbon forms directional covalent bonds leading to specific geometries, like the classic tetrahedral shape in methane, CH. That geometry comes directly from hybridizing the s and p orbitals, whose underlying shapes are those spherical harmonics.
So no spherical symmetry means directional bonding.
Precisely. And in transition metal chemistry, the way those non-spherical d orbitals interact differently with surrounding molecules or ions, the ligands, explains a huge amount of their complex chemistry, colors, and magnetic properties. That's ligand field theory, heavily based on d orbital shapes.
So this idea of quantum sphericity, how spherical symmetry can emerge from summing up these anisotropic directional components, is really fundamental.
It really is. Unsold's theorem is a beautiful example of how collective properties can be much more symmetric than the individual parts that make them up. It's key to understanding bonding and material properties.
This is really connecting a lot of dots for me. We see the same math, these spherical harmonics describing, wiggles on a classical ball and then these probability clouds in a quantum atom. But it feels fundamentally different. What's the core distinction? What's actually vibrating or there in the quantum case? It's not a physical wave, right?
That's the absolute heart of the classical to quantum shift, and exactly where our everyday intuition can trip us up. It's worth laying out the key differences side by side.
Okay, let's do it.
First, nature of the function. Classically, the wave function, let's call it capital psi, usually represents a real physical quantity.
Like the height of a water wave or air pressure.
Yeah.
Something you can, in principle, measure directly.
Exactly. It's directly observable. In quantum mechanics, the wave function, little psi, is a complex probability amplitude. You generally cannot directly observe itself.
Right, only its squared magnitude, which gives probability density.
Correct. Where you're likely to find the particle. A very different meaning.
Okay, function meaning is different.
What else? Second, energy. In classical systems with boundaries, you get discrete modes, yes, but often the amplitude of the oscillation, and therefore the energy stored in the wave, can vary continuously. You can have a gentle ripple or a huge wave.
Makes sense.
In quantum mechanics, for bound systems like an electron trapped in an atom, the energy levels themselves are quantized. Only specific, discrete energy values, n, are allowed.
The energy steps are fixed.
Fixed to steps.
Right.
Third, determinism. Classical physics, at its core, is deterministic. If you know the initial position and velocity precisely, you can predict the future state precisely.
Like calculating a billiard ball's path.
Right. Quantum mechanics is fundamentally probabilistic. The wave function gives you the probabilities of different outcomes if you make a measurement. You can't know everything simultaneously with perfect accuracy. That's the Heisenberg uncertainty principle.
Probability, not certainty.
Exactly. And maybe the biggest conceptual jump is the nature of the vibration or shape.
Yeah, this is the one I'm stuck on.
Classical vibration is a physical motion, an oscillation happening over time, a drum skin moving up and down.
Right.
But for a quantum stationary state, meaning an energy eigenstate, like an electron in a specific atomic orbital, 1s, 2p, etc., the probability distribution is static. It does not change with time at all.
Wait, static, not vibrating.
Not vibrating in the classical sense. The shape of the orbital isn't a physical object oscillating. It's a time-independent map showing where you are most likely to find the electron if you were to look, based on its energy and quantized angular momentum state.
The dumbbell shape of a orbital isn't wobbling around.
Not for a stationary state, no. Now, the wave function itself does evolve in time, but only by picking up a complex phase factor, e to the power of IET.
Okay, complex phase factor.
But when you calculate the observable probability density, you take the magnitude squared, IT, and that phase factor completely cancels out. EIT is just 1, so the probability density remains constant.
Ah, I see. The observable part is static.
Correct. Real time-dependent changes in the probability distribution, something that might look more like classical motion or oscillation, only happen when a quantum system is not in a single stationary state, but in a superposition of different energy states, or when it undergoes a transition, like emitting a photon.
Okay, wow. So the common thread is really the geometry, the constraints imposed by spherical geometry, and the need for well-behaved solutions lead to those integer indices nm. In both realms. That's the natural quantization.
Yes.
But the physical meaning of the function itself undergoes this dramatic, almost philosophical shift from describing tangible physical reality to describing probability in quantized properties like angular momentum.
Exactly. You've nailed it. And that underlying mathematical structure, the spherical harmonics being the natural language for spheres, that's why they are so powerful and just keep showing up everywhere.
Yeah. You mentioned they appear beyond waves and atoms.
Absolutely. We've taken this journey from classical vibrations to the quantum structure of atoms, seeing how the mathematical modes dictated by spherical geometry are the very same functions describing quantized angular momentum. But their usefulness is incredibly broad. They are essential whenever you analyze anything happening on or around a sphere.
Like where else, specifically?
Well, in cosmology, they are absolutely fundamental for analyzing the tiny temperature variations, the anisotropies, and the cosmic microwave background radiation.
The oldest light in the universe.
Exactly. Analyzing the CMB map using spherical harmonics tells us about the structure of the early universe, its geometry, its composition. The different use values correspond to different angular scales in the sky.
Amazing. What else?
In geophysics, they're used constantly to model Earth's complex gravitational field and its magnetic field. These fields aren't perfectly uniform, and spherical harmonics provide the natural way to map out their variations across the globe. Also for analyzing seismic waves traveling through the spherical Earth.
Okay, planets and stars.
And even in computer graphics. They are a fundamental tool for efficiently calculating how light interacts with objects in 3D scenes.
Really? Wow.
They're used for things like precomputed radiance transfer, PRT, and ambient occlusion, basically ways to represent and calculate realistic lighting and shadows much more efficiently than trying to trace every single ray. Spherical harmonics provide a compact way to store how light arrives from all directions.
Huh. Wouldn't have guessed graphics.
Also, electromagnetism. They're used to describe the radiation patterns from antennas, how energy radiates in different directions. This is called multipole expansion, closely related to spherical harmonics, also for solving potential problems around charged spheres.
So antenna design.
Yep. And you also find applications in medical imaging, like analyzing diffusion tensor MRI data, and in acoustics for modeling sound fields in rooms or around heads.
It's kind of wild, isn't it, it feels like?
Yeah.
From the smallest electron cloud to the gravity of the whole Earth to the structure of the universe's oldest light, there's one mathematical toolkit.
Born from waves on a sphere.
It just pops up absolutely everywhere. Why do you think that is? What's the deep reason?
It really does suggest something fundamental is going on, doesn't it? The elegant persistence of spherical harmonics and this underlying principle of sphericity across classical and quantum physics, across microscopic and cosmic scales. I agree, it feels like more than just a mathematical convenience or a neat trick.
Yeah.
It could be a fundamental clue, perhaps, hinting at a deeper underlying unity, or maybe a required structure in the physical laws that govern our universe, especially where rotation or central forces are involved.
It certainly makes you look at the wind a little differently, doesn't it?
Yeah.
You know, from the curve of a planet, maybe a bubble floating by, to the very shapes that define where an electron might be found inside matter. Spherical symmetry and these powerful mathematical functions are just silently, elegantly at work underneath it all.
Well said.
Well, thanks for joining us for this deep dive today. Hopefully it gave you a new appreciation for the sphere.